Module 1, the oceans of our planet, continental drift and plate tectonics. When you take a look at the shape of the continents of the world, you might begin to see something interesting. Even 400 years ago, scientists noticed something interesting as they stared at world maps. You see, the continental shapes seemed to match up like pieces of a puzzle. So some scientists began to suggest that there was a time in Earth's history when the continents may have been connected to each other. As time went on, other similarities besides shape began to be discovered. Coal deposits and unique fossil deposits were found on opposite coasts of the Atlantic Ocean and other areas. These deposits were so similar that they could have been parts of a greater whole. As more information like this was gathered, a German geophysicist named Alfred Wegener came up with the hypothesis of continental drift. He tried to explain the data by suggesting that at one time in Earth's history, all the continents were part of a large supercontinent called Pangaea. Then, something caused Pangaea to break up, and the broken pieces, or continents, slowly moved away from each other to their present positions we see them in today. Well, at that time, the idea of continental drift was not accepted as a viable one because there was not any scientific explanation for the mechanism that could cause huge land masses to move. But as more evidence was discovered to support Wegener's hypothesis, scientists began to agree that the continents of the world actually do drift. And the process that moves them is called plate tectonics. Plate tectonics is a process involving the movement of large plates on the Earth's mantle. The idea is that the Earth's crust is divided into large irregular plates floating on the plastic rock mantle. Scientists currently believe that the radioactive decay of elements within the mantle create heat. As the heat rises up through the plastic rock, it causes currents to form, which move the plates floating on top. It's kind of like a broken rectangle of styrofoam floating in a swimming pool. The original rectangle would represent Pangaea, and the broken pieces would be the plates, floating away from each other as the current of water molecules carries them. The faster those water molecules moved, the faster the styrofoam pieces would float apart. Well, the heat generated from radioactive decay of mantle elements could cause the compounds within the plastic rock of the mantle to cause the continents to float away. This is our present understanding of the location of the plates of the Earth's crust. Where they meet, there are two types of geological structures that could exist: a mid-ocean ridge system or a trench system. The mid-ocean ridge system consists of a continuous chain of underwater volcanic mountains encompassing the Earth. So these ridges extend all around the Earth. In fact, they are the largest geological features found on the planet. I'm standing in the center of the Mid-Atlantic Ridge. Now, the ridge is where two of the Earth's plates meet each other. The Earth is made of a crust, and those crust is broken up into plates, and those plates float on the magma of the Earth. And as they float, they move a bit. And in the Mid-Atlantic Ridge are where two plates are meeting and separating from each other very slowly at a rate of about 2.5 centimeters per year. As they separate, some of the magma comes up, creating mountains and volcanoes. And the reason why I'm not underwater in the Mid-Atlantic Ridge is because I'm on the island of Iceland. Iceland is a volcanic island created from that ridge separating from itself, creating lots of volcanoes. And the volcanic rock you're seeing behind me is from older eruptions from the ridge separating. This is actually one of the longest mountain ranges in the world, which travels under the Atlantic Ocean. Ridges and trenches experience a lot of geologic events, including earthquakes and volcanic activity. Earthquakes tend to be more common around ridges, and active volcanic events occur more often near trenches, though many of these events overlap. Additionally, an interesting phenomenon was discovered around mid-ocean ridges. You see, when you hold a magnetic compass, the needle points to magnetic north, which is a point near the northern tip of the Earth. But it wasn't always that way. Geologists have learned that there were times in the history of the Earth when its magnetism was reversed. So during a reversal time, a compass would point to the South Pole instead of the North Pole. How did they learn this? Well, in molten rock, there are lots of materials, including small magnetic particles. These particles will always align themselves toward magnetic north. And as the rock cools and hardens, the particles are frozen in their positions, pointed to wherever north was at that moment in history. It turns out that there are many layers of igneous rock, which is rock that forms when molten rock cools, where the magnetic particles are pointing south instead of north. That means that at that time, the Earth's magnetic field was flipped as compared to the way it is today. We call the particles pointing the, quote, wrong way, magnetic anomalies. As scientists are sampling rocks near the mid-ocean ridges, they are finding there is a pattern. There are groups of rock located in bands on either side of the ridges with alternating magnetic orientations. So some bands have rocks with magnetic particles directed to the north, and other bands have rocks with magnetic anomaly particles directed to the south. And these bands are symmetric around the mid-ocean ridge, like a mirror image. This suggests that the bands of igneous rock on the ocean floor were produced from molten rock at different times in history. This is evidence that the seafloor in these areas was likely not formed at one single time, at least where these bands are. So we could hypothesize that these sections of the Earth's crust near the mid-ocean ridge are moving away from each other, forming a crack. That crack or separation is a rift between the plates. If the plates are moving away from each other, the area of the rift doesn't have as much pressure on the mantle below it. That decrease in pressure can cause the mantle to melt enough to turn liquid and then rise up through the rift. When this happens, we call the melted mantle material magma, and it pushes its way up through the rift, creating a ridge. It eventually cools and creates new oceanic crust. This process is called seafloor spreading. Seafloor spreading is the process that creates new seafloor as plates move away from each other at the mid-ocean ridges. Seafloor spreading explains many of the features we see around ocean ridges. With this process, the crust at the ridges then would be newer than the crust further away from the ridges, so that newer crust would have less time to accumulate ocean floor sediment. This could explain why in many areas the sediments of the ocean floor are thicker as you travel away from the ocean ridges. Similarly, seafloor spreading also could explain that pattern of magnetic rocks mirrored on each side of the ridges. As magma seeped up through the rift, it cooled, fixing the magnetic particles in position, pointing wherever magnetic north was at that time. So summing up, seafloor spreading and plate tectonics are believed to be closely related to each other. They suggest the Earth's crust is divided into irregular plates, which float on denser mantle material below them. Where the plates meet is either an oceanic trench or oceanic ridge system. Some plates in the world are made up of both oceanic and continental crusts. As two plates move away from each other, new ocean crust is formed. And as more and more is formed at the ridges, it carries whatever collected sediments and land masses are on it. But you need to know that, at least in the present, this process is very, very slow. Today, the plates move at a rate of 2 to 18 centimeters each year. So let's look at what we have now. The Atlantic Ocean at some places is up to 1,000 miles wide. It is postulated that it is a completely new ocean, forming when Pangaea split apart. If seafloor spreading occurred at the rate we see today, the Atlantic would have taken millions of years to get to its present dimensions. But there is no strong evidence that the spreading rate has been consistent. We know there are several physical parameters on Earth that have changed over the course of history, including the Earth's magnetic field. So there's no reason to believe the Atlantic seafloor has always spread at its current rate. If there was a catastrophic event, for example, the plates could have moved more rapidly. We have evidence of faster movement too. A good example of this is within the country of Eritrea. In 2006, a 60-kilometer crack opened up over the course of just 10 days. It continues to expand, and some scientists suggest that it will eventually form a small ocean, possibly causing the Horn of Africa to fall away from the continent and form an island.